The Atwood Machine. Figure illustrates an Atwood machine. Find the linear accelerations of blocks A and B, the angular acceleration of the wheel C, and the tension in each side of the cord if there is no slipping between the cord and the surface of the wheel. Let the masses of blocks A and B be 4 kilograms and 2 kilograms respectively. The moment of inertia of the wheel about its axis be 0.22 kilograms meter square and the radius of the wheel be 0.12 meters. Okay, so as you can see here, so I'm assuming that block A is accelerating down, block B is accelerating up, the wheel is turning in the clockwise direction, so this is the direction of angular acceleration. So if we set up our coordinate system here, this angular acceleration would have a minus k hat direction using the right hand rule. So if we curl our fingers in the direction of alpha, the thumb points in minus k hat. Okay, so if I look at the free body diagram of block A, that's this block, there will be a tension T1 acting on it, and there will be the weight MA times G that is pointing down. If I look at the free body diagram of block B, there will be a tension T2 acting up and MB times G acting down. So these two free body diagrams give me the following result. Net force acting on the y-axis on MA is going to be equal to, so let's write this in minus j hat direction because that's where I'm assuming acceleration is pointing. So MAG minus the tension T1 is equal to mass of A times the common acceleration A. And let's call this equation 1. And when I look at the free body diagram of block B, B is accelerating up. So if I write the net force on the y-axis in j hat direction, this is T2 minus MBG. This is equal to MB times the linear acceleration A, and let's call this equation number 2. Okay, now let's concentrate on this wheel. So I said that on block A, this T1 is pointing up, therefore it's pointing down on block C, and T2 is pointing up on block B, therefore it's pointing down on block B. So on the wheel C, so you can see that this T2 pointing up on B would correspond to a tension T2 pointing towards the left on the wheel C. So let's make this correct. Okay, so this T2 is pointing to the left and T1 is pointing to the right in this setup. So because I have called this one T1 and this one T2. Okay, so if I write the net torque acting on this wheel, the net torque acting on the wheel, now R cross T1 is in the negative k hat direction, so I will have minus R T1 k hat direction, and then I will have R cross T2 in positive k hat direction, so plus R T2 k hat. So the net torque acting on this will be R parentheses T1 minus T2 minus T1 in k hat direction. So my acceleration is in a minus k hat direction. So this is going to be equal to minus I alpha k hat. Why? Because the angular acceleration alpha is pointing in the clockwise direction. So if alpha is the magnitude of this, then I would have a minus sign here. Okay, so this gives me T1 minus T2 times R is equal to I alpha. And we know that the linear acceleration is linked to the angular acceleration alpha as alpha times R. So alpha is equal to A divided by R. So this is going to be equal to, so let's call this equation number 3. This is equation number 4. And I want you to notice that T1 and T2 cannot be equal here. So note that T1 equals T2 would imply zero torque. So this would be problematic. Zero torque on the wheel C. So these tensions cannot be equal. Okay, so let's rewrite equation number 1 here. Equation number 1 is MAG minus T1 equals MAA. So we can isolate T1. So this is going to be rewritten as T1 is equal to MA parentheses G minus A. So MA parentheses G minus A. And likewise, we can write for T2 here, MB parentheses A plus G. So that's equation number 2 can be rewritten as T2 equals MB times G plus A. All right. So these two equations put together will give us T2 minus, or write it this way, T1 minus T2 is equal to MA G minus A minus MB G plus A. Alright, so T1 minus T2 is also equal to I alpha over R, which is I alpha over R, which is equal to IA divided by R squared if I substitute for alpha A over R. Okay, so I can now isolate acceleration here. So let me see what I have for acceleration. So in acceleration parentheses, I have minus MA and minus MB on the left hand side. And then on G parentheses, I have MA minus MB. This is equal to IA over R squared. So let's put everything together on the right hand side for acceleration. So we will be left with G times MA minus MB on the left hand side, G times MA minus MB is equal to acceleration times MA plus MB plus I over R squared. So we can now write our final result for acceleration symbolically. Acceleration, the linear acceleration, is equal to G times MA minus MB divided by MA plus MB plus I over R squared. So we can substitute for G 9.8 meters per second square. What was the mass of A? So let's see, A was 4 kilograms, B was 2 kilograms. So it's going to be 4 minus 2 divided by 4 plus 2 plus moment of inertia was given as 0.22 divided by the radius squared. And what was the radius? The radius of the wheel is 0.12 meters. So it is 0.12 parentheses squared, and this gives us our final result, 0.921 meters per second square for the linear acceleration of the system. Now we can find the angular acceleration. Alpha is equal to A over R. So this will give us the linear acceleration 0.921 divided by 0.12. So the angular acceleration of the wheel is 7.68 radians per second square. And from equation number 1, we can substitute for MA, G, and A. So T1 is equal to MA, which is 4 kilograms, times 9.8 minus the linear acceleration 0.921. We find T1 to be 35.5 newtons. So it is MAG minus A. And for T2, from equation number 2, we have T2 equals MB times G plus A, which is 2 times 9.8 plus 0.921, which is 21.4 newtons. So the tension on the right hand side is 35.5 newtons, on the left hand side is 21.4 newtons. So we have a net torque in the clockwise direction acting on this, and this is basically on an axle here, so you might be wondering where is this net force being balanced, T1 minus T2. So that would be balanced by the axle on which this wheel is turning, so there would be a contact force there. Okay, so to summarize, we have Atwood's machine that's consisting of two blocks of masses 4 kilograms and 2 kilograms. Mass A is greater than mass B. The system will be accelerating in the in a sense that A would be going down, B would be going up, and the block and the wheel C would have an angular acceleration in such a way that it would be turning in the clockwise direction. And from free body diagram of block A, we have two forces acting on it, tension T1 and its weight. The net force is ma times the linear acceleration A. This is the common acceleration of A and B. So B would have two forces, T2 and mbg, acting on it. But the direction of acceleration on B would be pointing up, on A would be pointing down. So you can see here. So I have written the first equation for block A in the minus j hat direction. So MAG minus T1 is MAA. And for block B in the plus j hat direction, T2 minus MBG is MBA. And for the wheel C, if these are the tensions acting on B and A, we would have their counterparts acting on the wheel C. T2 would be pointing down on the left side. On the right side, T1 would be pointing down. So on the top of the wheel, we have T1 pointing to the right, T2 pointing to the left. If we write the net torque acting on this, R cross F, so the distance, perpendicular distance from the pivot point towards the application point of the force multiplied with T1 that's going to be using the right hand rule in minus k hat direction. So we point towards the application point, curl our fingers towards T1, the thumb points into the page. And for T2 we have the opposite torque, RT2 k hat. But where is the direction of the angular acceleration? So this is supposed to be accelerating in the clockwise direction, so alpha would be in minus k hat direction, so minus I alpha k hat. So this would give us an equation between the tensions and alpha, and we also know that in rolling without slipping, the linear acceleration A would be linked to alpha as alpha times r. So putting these equations, the equations we obtained from free body diagram of A and B, from the free body diagram of wheel C, considering the torque effects, of course there are forces on the axle here, as I said, but those will not contribute to the torque. And by putting these together, we can obtain the linear acceleration. Then alpha is A over r, and once we know A, we can substitute in equation 1 and 2 to find what the values of T1 and T2 should be.